Okay, well, for rotation, we're going to say that the work done is F perpendicular delta S, which looks totally like F parallel delta S for motion on a straight line, right? Let's say we're in rotation now. And why do we use F perpendicular? Well, it's pretty clear that if the vector from here to here, that would be called our radial vector. It's from our axis of rotation to the point of application of the force, okay? It's only the component of the force perpendicular to that radial vector that does any work. And this example should make that fairly clear. Let's give you a way of understanding it. So F perpendicular is perpendicular to the radial vector. Our general picture for a rotational object isn't a beam, but the principles we learn in talking about a beam apply everywhere, okay? So we've got some extended object rotating about this axis, okay? An axis through this point, or maybe just through this point, right? And we apply a force. Okay, so we apply some force. Let's use a different color. We apply a force here. Okay. Well, we have our radial vector R here. That's our radial vector. From the axis of rotation to the point of application. Point of application, implicitly the point of application of the force, right? Don't want to have to write out all those words, but hopefully that's understood, right? So what do we get? Well, is that going to tend to rotate this object? It's going to rotate it clockwise or counterclockwise?
Clockwise.
Clockwise. You know, it'll be that way, right? It's obvious. Okay, you've been watching forces rotate things for many labs now, okay? And if you remember what clockwise is, it'd help if we used real clocks instead of these digital things, but you know, people still kind of remember which way is clockwise, right? Yeah, I still think students today are just really disadvantaged by not having a clock to stare at. When's this class going to be over?
With that in note, I said the wrong one, I meant counterclockwise.
The what?
With that in mind, I said the wrong one, I meant counterclockwise.
Actually, it is counterclockwise. See, they don't have clocks on the walls anymore. I can't tell. Duh. Okay? It's counterclockwise. It's the positive direction of rotation. Okay? That's the way I'm used to thinking about it. No excuse. Okay. Now, what percent of the magnitude of this force do you think actually contributes to the rotation?
Something like, what, about 60%?
60%? Okay, I'll go with 60%. I think in 60, 70 range. Okay, maybe even 80. Yeah, I'm looking at it from here. I can't really see that angle. If it's 45 degrees, it's about 71%, right? So it's somewhere around 45 degrees, maybe a little more, maybe a little less. Okay? Did I say 71 degrees? 45 degrees. Okay?
You said 45 degrees.
Okay, so it's around 70%, give or take. So anything from 60 to 8 I'd regard as a decent estimate. Okay, well, we can sketch the components of this force, right? Relative to the R direction, you project the force down here, you get F parallel. And if you project down here, you get F perpendicular, right? Okay? And the work done if you have an angle, go through a small angle d phi, it's just going to be F perpendicular times R d phi, right? In other words, same thing I wrote here. No. Well, I didn't. Yeah. It can't be this, but your delta S is your R d phi, right? So, all right. Okay, well, we rewrite this as tau d phi, that's the Greek letter tau, okay? So whatever you do, well, it's not T, it's tau. It's wavy little, fancy little, okay? T type thing. And this is called, anybody know what that's called? Called torque. Okay? Now, there's an immediate consequence of what I've done here. First of all, your work is tau delta phi. Okay? If you have a constant torque through some angular displacement, okay? Or you integrate from phi 1 to phi 2 the torque with respect to phi, if it's not a constant torque, okay? And most examples we'll do soon are going to be constant torque, okay? Well, there's a lot more that we can use this idea of torque to do. For example, turns out that your angular acceleration let's put it this way. It looks more like Newton's second law. I mean, what I was about to write is just a rearrangement, but let's say that torque is I times alpha. What's I?
Impulse.
Huh?
Impulse.
It's moment of inertia. We talked about it last time. Assignment today asked you to do moment of inertia, right? It's what we put into the formula 1/2 I omega squared to get the kinetic energy. Okay? That's the way we've defined it, not necessarily the way your book defines it, but I think it's fairly close. Okay? So this moment of inertia, this is angular acceleration. Does that look like Newton's second law? Sure it does. What does torque do to an object? It accelerates it, right? Well, what accelerates objects along a straight line? Force. Net force, right? And actually, I probably ought to put a net on here. Okay? Now, what's moment of inertia?